The first topic we're going to look at in chapter 3 is that of invertibility of matrices. Up to this point, we've used the Gaussian elimination algorithm to find solutions to linear systems. We're now going to investigate another way to find solutions to equations of the form ax equals b, specifically in this case when A is a square matrix, so it has the same number of rows and columns. So what we're going to be looking at here is specifically when A is an n by n or a square matrix. To get started, let's look at some familiar examples. So this example here, 2x equals 6, is not even, an example from linear algebra, just sort of a basic algebra example that hopefully we are all fairly comfortable solving at this point. So the way we might go about solving this, right, 2x equals 6, we might divide both sides of this equation by 2. And so the 2's would cancel here, and we're just left with x equals 6 over 2, or 3. Instead of dividing both sides by 2, I want to view this actually as multiplying both sides by 1/2. So if I were to do that, I multiply, 1/2 over here, and then 1/2 over here. Squeezing it in on the left, I do want to be specific and multiply it by 1/2 on the same side. This doesn't matter, of course, for regular multiplication of numbers. We can multiply regular real numbers in any order we want, but it does matter for matrices. So I do want to get used to sort of multiplying, both sides of the equation on a particular side. So what happens on the left-hand side is we have 1/2 times 2x. We can kind of reassociate the 1/2 times 2, and then we have our x equals 1/2 times 6, which is 3. And then the 1/2 times 2 becomes 1. So we have 1 times x equals 3. And what's special about 1? Well, 1 times anything is just that thing. So x equals 3 is our solution. So we can solve this by multiplying both sides by 1/2. In some classes, you may have heard the term of a multiplicative inverse. So we would actually say that 1/2 is the multiplicative inverse of the number 2. What does that mean? It means exactly what we wrote basically earlier, that 1/2 times 2 equals 1. So a multiplicative inverse for real numbers is a number that when you multiply it by that other number, you get the number 1. The other thing I want to remind you of is some notation. So we could write the number 1/2 actually as 2 raised to the minus 1 power, right? When you raise to negative exponents, we can write those as 1 over that number to sort of the positive version of that exponent. So 2 to the negative 1 is 1 over 2 to the 1, or 1/2. So let's keep that minus 1 in the exponent notation in mind as we move forward here. So what are we seeing? 1/2 times 2 equals 1. We can write that as 2 to the minus 1 times 2 equals 1. So 2 to the minus 1 is sort of the multiplicative inverse of 2. This minus 1 notation being used in the exponent being used for inverses is something we may have seen in like a calculus class or an algebra or pre-calc class, being used for inverses of functions. So this sort of notation for inverses is something we have seen before, and it kind of comes from this idea of real numbers where raising to the negative 1 power gives us the multiplicative inverse. So let's look into matrices now. Consider this example, ax equals b, where a is 1, 2, 3, 5 times the vector x equals some vector b in R2. Okay, and so our goal is to solve this. We could, of course, kind of solve this using Gaussian elimination, as we've seen before, writing this as a system, and then the augmented matrix would end up looking like this, and we row reduce, and sort of we're on our way. That's what we've done previously, but we're going to learn a new method here. Let's consider the matrix B. Sort of seems to come out of nowhere here. B is negative 5, 2, 3, negative 1, but our claim is that B has the property that it is the inverse of A. So what does that actually mean? Well, what I want to see is that if we multiply B by A, and we might we might use this notation. I'm actually back up for a second before we get to that. So let's try multiplying b times a and see what happens. So b times a, -5, 2, 3, -1, times a, 1, 2, 3, 5. Okay, and we do this out. So -5 times 1 plus 2 times 3, so that's -5 plus 6, so that's a 1. And then -10 plus 10 is a 0. And then 3 minus 3 is a 0. And then 6 minus 5 is a 1. So we can actually see here we get this matrix 1, 0, 0, 1, which we may recall is called the identity matrix, which we denote as I. So this is the 2 by 2 identity matrix. And what's special about the identity matrix? Well, let's look at what happens when we multiply I by some vector. Let's look at I times some vector x, where x is maybe just the vector x1, x2. Let's do this for R2. So this would be 1, 0, 0, 1 times x1, x2. Okay, and if we do this out, we end up getting just x1, x2. So what's special about the identity? Well, when we multiply it by a matrix or a vector of the appropriate size, we recover that same matrix or vector. So in this case, I times x just equals x. And so if we're trying to solve the equation ax equals little b, and what we've just discovered is that this matrix big B has the property where when we multiply it by A, we get the identity. Let's see what happens when we multiply both sides of this equation by big B on the left. So we'll have B times AX equals big B times little b. We can reassociate that matrix multiplication on the left-hand side. So we have BA times X equals big B times little b. But BA, we discovered up here, is the identity matrix, right? That's what we kind of looked at up here, that BA is the identity matrix. So this becomes just the identity matrix times X equals B times B, or said another way, just X equals big B times little b. So if we're trying to solve for X, we can just take big B and multiply it by little b. And so let's do that. Let's look at big B times little b. So give myself some space over here. Okay, so big B times little b is x. So that's -5, 2, 3, -1 times 7, 18. Okay, and so what do we end up getting? -5 times 7, I guess that's -35, plus 2 times 18 is 36. So -35 plus 36 is 1. And then 3 times 7 is 21, minus 18, I guess that is 3. So this tells us what x is. It's just 1, 3. And if we had gone through this Gaussian elimination, right, and sort of row reduce this, which wouldn't have been so much work, mind you, but if we had done that, this would have row reduced down to precisely this matrix. So this is kind of another way of solving this kind of a system. We're going to see other uses for this sort of thing as well, but this is certainly one use. Okay, and so kind of the idea here is that we might write B using this inverse sort of notation, A with this -1 in kind of the exponent. So B is this A inverse. And then the idea is that, we can multiply both sides on the left by that A inverse. And we end up getting the solution for X is just that A inverse, or that B, times 718, and we get our solution. Okay, so just to sort of go through it all again, if you multiplied A by that B or by that A inverse, you'd get the identity, and that's kind of the key. Okay, and this is just kind of recapping everything we did earlier, right? So AX, we would multiply by A inverse. I'm not going to go through everything again, but we would multiply both sides by A inverse on the left. Okay, and so we'd get x equals A inverse times little b. Onto our definition. So we would say that an n by n matrix A is invertible if there is a matrix B such that AB equals BA equals the identity, where I is the identity matrix. We do make a point here to do this multiplication in both orders, right? That, AB and BA are both equal to I. This is not a trivial thing. When it comes to matrix multiplication, we know it is not commutative. And so the fact that AB and BA are both I is certainly something to think about here. And the matrix B is called the inverse of A. We denote it with this notation, this A with a little -1. So that's A inverse. I'll note that we say a matrix is called invertible if there is this matrix B. This implies that there is a situation potentially where a matrix is not invertible, where there is not such a matrix B, right? Notice we don't say, the inverse of matrix A is always this. We say if there is a matrix B. So we're going to be exploring this idea in a future video where maybe we could have a matrix that is actually not invertible. We were kind of given that matrix B, which ended up to be the inverse earlier, for the matrix A, 1, 2, 3, 5. But how can we actually find that, right? If we want this to be a useful tool, we most likely won't just be handed this inverse. We'll have this matrix because we have our original equation, but can we find its inverse? So for a 2 by 2 matrix, 1, 2, 3, 5, suppose A inverse is just the matrix A, B, C, D. So we know that A times A inverse has to equal the identity, which would mean 1, 2, 3, 5 times A, B, C, D would have to equal, the identity. And so if we were to do this multiplication, we would get a system of equations that can be solved for A, B, C, and D. So let's see if we can go through that. Okay, so we have 1, 2, 3, 5 times A, B, C, D. When we do that multiplication out, we would get A plus 2C. This is a 2 by 2 matrix, right? If I'm multiplying A times what I'm hoping to find, this A inverse would be a 2 by 2 matrix. So that's A plus 2C, and then B plus 2D, 3A plus 2C, plus 5C, and 3B plus 5D. And that supposedly should equal the identity 1, 0, 0, 1. But when are two matrices going to be equal? Precisely when their components are equal. So we would need A plus 2C to equal 1. We would need 3A plus 5C to equal 0. We need B plus 2D to equal 0. And we would need 3B plus 5D to equal 1. And what we have here is a system of equations. We've got 4 equations and 4 unknowns. However, what we actually have is really 2 sets of 2 equations and 2 unknowns, because the equations with A and C don't interact with the equations for B and D. So we can actually kind of solve these as 2 separate systems with 2 equations and 2 unknowns. So the augmented matrix for our AC system would look like that. The augmented matrix for the BD system would look like that. And these actually have identical coefficient matrices. And so, as we're solving these, we're going to be doing the exact same row operations. And so kind of the trick to doing this a little bit quicker is to do all of those operations just one time, but kind of solve both of these systems at the same time. And so how we can do that is by writing 1, 2, 3, 5, and then putting both of these columns, both 1, 0 and 0, 1, to the right of that line, kind of augmenting with 2 different right-hand sides simultaneously. And what you might notice here is that we've kind of got our original matrix A augmented with the 2 by 2 identity matrix. So let's try and solve this now like we would solve a regular system of equations. I'm going to rewrite it over here just to give myself a little bit more space. Okay, and then we can erase all this. And so we're going to go through our reduction algorithm now to, try and solve these two sets of, systems of equations. So we might start by doing an R2 minus a 3R1. So we'll have a 0. 5 minus 6 is a -1. -3, 1. Can then do a negative R2. To get that. And then we can do an R1 minus a 2R2. So we get 1, 0. And then 1 minus 6 is -5, 2, 0, 1, and 3, -1. Okay, and so we've solved both of these sets of systems, and what we've actually found is, kind of focusing our attention on this first column, which in, this matrix here, this system here represents A, and in this system here represents the coefficients of B. So this is sort of A or B, depending on what we're looking at, and this second column represents C or D. And so what we found is that A equals 5, B equals 2, C equals 3, D equals -1. And so the inverse that we just discovered, this A inverse, is the matrix 5, 2, 3, -1. And if we go back, we actually see that exact thing here. -5. Oh, did I say that right? This should have been a -5. -5, whoops, -5. There we go. -5, 2, 3, -1, which is precisely that matrix that we saw earlier. Okay, so the process is to, begin with our matrix A, augment it with the identity matrix, and then apply row operations until the left-hand side becomes the identity matrix. And what we'll be left with is sort of the identity matrix on the left and the inverse on the right. We're going to introduce this more formally in a future video, but that's kind of the idea. So we row reduce, we start with our matrix augmented with the identity, and then we row reduce until we get the identity on the left, and what's going to be left on the right is that inverse. And hopefully this example gives you some insight as to why that's true. Again, we're going to be diving into this a little bit more formally in a future video.